Alright, so the topic of discussion in 3.4 is related rates. So this is going to be a little bit of applications of derivatives. So let's get started. As a way to kind of introduce this concept, let's consider the following scenario. So suppose that we have an upside down cone filled with water and that the cone has a hole at the bottom. So, you know, something like this, I suppose. Maybe a little tiny hole at the bottom. You know, something like that. Okay. And it's filled with water, so maybe there's like water or whatever in it. But it's draining out of this hole, right? Okay, so as the water drains, the volume, height, and radius of the water in the cone change. That is, they're each functions of time t. Now those quantities, volume, height, radius, they're all related by the formula for the volume of a cone, right? Like if you're thinking about the volume of water in the cone, you would use the volume formula, V equals pi over 3 r squared h. So to find the rate at which the volume, height, and radius are changing, we can differentiate this formula with respect to t. And so this is all going to be implicit differentiation because we're assuming that each of these are changing in time, so they're all functions of t, right? So the volume, the radius, and height are all functions of t. So doing implicit differentiation on this, dv dt is going to be pi over 3 times derivative of, we're going to have to use product rule here, right? So derivative of r squared is going to be 2r dr dt, and then times h, okay, plus, and maybe I should use some parentheses, but plus the first one, r squared, times the derivative of the second one. Derivative of h is just 1 dh dt, so times 1 times dh dt. We could clean that up a little bit, I suppose. I mean, not much, but we could call it pi over 3 times 2rh dr dt plus r squared dh dt. Okay. Now, these quantities, right, dv dt, dh dt, dr dt, right, so the rate, those represent the rate at which the volume, height, and radius are changing. And they're related, right? They're related via this formula right here, and so we call them related rates. So we're going to look at some related rates problems. The first one, the first example I want to look at is just to make sure that we understand the mathematics, but then we'll look at some actual, you know, scenarios. So let's look at this first example. It says, suppose that x and y are differentiable functions of t and are related by the equation y equals x cubed. Find dy dt at time t equals 1 if x equals 2 and dx dt equals 4 at time t equals 1. Okay, so let's do this, right? So we're starting with y equals x cubed. We want to find dy dt. Okay, so we need to differentiate this equation with respect to t. So we're assuming that y and x are both functions of t, which means that we're going to be doing implicit differentiation here. So derivative of y is just 1 times dy dt. Derivative of x cubed is 3x squared times dx dt. Right? Okay, so it's a little subtle. It's like if we want, so maybe I'll pause for a second and just say, like, obviously if we were finding dy dx, dy dx would just be 3x squared and that's it, right? But we're not looking for, we're not differentiating with respect to x. We're differentiating with respect to t, all right? And so we're assuming that y and x are both functions of t, and so we have to use chain rule, right? So we're going to say y is dy dt, the derivative of y is dy dt, right? Derivative of x with respect to t is 3x squared times dx dt. Okay? Alright, so, okay. Now we want to figure out what dy dt is when x is 2 and when dx dt is 4. So that's pretty easy, right? We just plug that stuff in. We're going to say dy dt when x is 2 and dx dt is 4, right, equals 3 times 2 squared times 4. Okay? 2 squared is 4. 4 times 3 is 12. 12 times 4 is 48. So there you go. So this is dy dt at time t equals 1. Alright? Okay, so that's that. Now let's look at an actual scenario. By the way, like obviously I'll have a link to these notes in the module where I post this video. But so number 2 here says, assume that oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the radius of the spill is 60 feet? So at first glance that might seem kind of complicated, but I think if you draw a picture and then you start trying to relate these things to one another, it becomes pretty easy. So we know that the oil is spilling out in a circular pattern. So we've got this circular spill. I don't know why I'm doing a dotted line, but whatever. Okay, so we have this circular spill. I think I did a dotted line because I'm assuming that like it's growing still. So I don't want to draw like a definite boundary, I guess. It doesn't matter. But okay, so it's spreading out in a circular pattern at a constant rate of 2 feet per second. It says, how fast is the area of the spill increasing? How fast is the area increasing? So we want to find like the area of this circle, and then we want to find how fast it's increasing. So we probably are going to differentiate with respect to time, right? With respect to time t. So first of all, let's figure out what is the area of this circle, right? Well, the area of a circle is pi r squared. So if I want to figure out how fast the area is increasing, well then I need to differentiate so that I can find out what dA dt is, right? That's going to be how fast the area increases. So I'm going to differentiate with respect to t. This is going to be pi times 2r times dr dt. Okay. So now let's see if we can figure out what to plug in here, right? dA dt is what I want. That's how fast the area is increasing. So so that's good, but I need to have something to plug in for r, and I need to have something to plug in for dr dt. So let's go back through the problem and see if it tells us. So we assume that oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. Okay, so that's a rate, right? That's 2 feet per second. That's dr dt. That's how fast the radius is increasing with respect to time. So this 2 feet per second, that's dr dt. Okay, and it says how fast is the area of the spill increasing when the radius is 60 feet? Okay, so that's the radius, right? So that's the radius. So we can plug these things in. We can say this is pi times 2 times 60 times dr dt, 2. Okay, so 2 times 60 is 120, times 2 is 240, so this is 240 pi. I guess we might want to figure out the units. This was 2 feet per second, right? And this was feet. So I think we have 240 pi feet squared per second, right? Or square feet per second, right? So 245 square feet, or it's 240 pi square feet per second. That's how fast the area is increasing. Let's see about how much that is. 240 times pi. That's about 754, we'll say. It's about 754 square feet per second. So there you go. So that's that. Okay. Now something to point out about this is notice that the area is, even though the radius is increasing at a constant rate, the area of the circle is not increasing at a constant rate, because when the radius is you know, let's say, you know, 1 foot, and then it increases to 2 feet, right? That's going to double the area. But when it's 39 feet and then increases to 40 feet, that doesn't double the area, right? So anyway, so the area is not increasing at a constant rate, even though the radius is increasing at a constant rate, which is why we have to go through all of this calculus in order to figure out how fast the area is increasing. I don't know if you'd be able to do this problem without calculus. I mean, maybe you could. I'd have to give it some thought. But anyway, so that's that. Let's look at another one. So number 3 says, a baseball diamond is a square whose sides are 90 feet long. Suppose that a player running from second base to third base has a speed of 30 feet per second at the instant when he is 20 feet from third base. At what rate is the player's distance from home plate changing at that instant? Okay, so let's draw this. I'm not going to draw it as a diamond, I'm just going to draw it as a square, since it's really just a square tipped on its side, but it'll be easier for me to draw this way. So, so I'm going to call this like home, right? So that's home, which means this would be first base, second base, and third base. Okay? And it says that the sides are 90 feet long, so each of these things is 90 feet. There you go. Put the units on there. But it's 90 feet all the way around. Whoops. 90. Okay. And then we have a player running from second base to third base at a speed of 30 feet per second. Well, or at least that's how fast he's going when he's 20 feet from third base. And the question is, at what rate is the player's distance from home plate changing at that instant? So here's what I'm going to do. So let's say that the player is, you know, right here. We're looking for the distance that the player is from home. We're not necessarily interested in the distance he's going to travel, because of course they would have to go to third base before going home, right? They would go around this way. But we're just asking about the direct distance from home to where he is, right? So that would be that point right there, or that distance right there. I'm going to call this h, because it's the hypotenuse of a right triangle. Okay, so I'm going to call it h. So this side is h, this side is 90, and this side is, well, we're interested in how fast h is changing when this distance is 20 feet. But we can't plug in 20 yet. So we're just going to call this thing, I'll call this thing maybe a. Because we need to have a way to relate all of these quantities together before we differentiate, right? Before we start plugging in specific values, right? So before we start plugging in specific numbers, we need to just have a way to relate all these things, right? So because this distance is changing, right? So A is changing with respect to time. 90 is not going to change, okay? Because the player is only running from second to third base. So 90 is just going to remain 90. But A is changing and H is changing. So anything that's changing, we need to find a way to write down a formula to describe how the changing things are related to each other. Before we do the calculus on it. Okay? So let's see. Can we write an expression now for that relates these things together? Well, yeah, I mean, if we were trying to find h, we would just use Pythagorean Theorem, right? We would say a squared plus 90 squared equals h squared. And that's all there is to that. I'm going to rearrange things a little bit and say this is h squared equals a squared plus 9 times 9 is 81, so 8100. Okay. Now I want to figure out how fast h is changing, right? I want to figure out how fast the rate dh dt. So I'm going to go ahead and differentiate both sides of this equation with respect to t. So differentiating h squared with respect to c, I'm going to get 2h times dh dt. And then on the left-hand side, I'm going to get 2a times dA dt. And 8100, well, that just goes away, right, when I take the derivative. So now, what do I need to do in order to solve for dH dt? Well, for one thing, let's go ahead and divide both sides by 2h. So I'm going to say dH dt is, well, when I divide by 2, the 2's cancel. So I'm just going to get a over h times dA dt. So what do I need? Well, I need to know dA dt, I need to know a, and I need to know h. And I'm in luck because if we go back and read through the problem, it says, suppose a player running from second base to third base has a speed of 30 feet per second. That's dA dt, right? That's how quickly a is changing. It's changing at a rate of 30 feet per second when he gets to this point. So, so that's dA dt. So this thing right here is dA dt. He's running that fast at the instant when he's 20 feet from third base, so that's A. Okay. I need to find h though, right? Because I also need to know what h is at that moment. So, so I'm going to draw my little right triangle again. I have h, I have 90, and this time I'm going to go ahead and plug in 20 for a so that I can solve for h. Right? And actually, we've already set up the equation here, haven't we? Right? So we can say, well, h is going to be the square root of a squared plus 90 squared. So let's see. 20 squared is 400. And 90 squared we said was 8100. So that's 8500. I don't think that's a perfect square. It's not, but so this is equal to 10 times the square root of 85. So that's h, right? That's h at the instant when a is 20. Okay? Okay, so coming back and plugging that in up here. So so I'm going to say, all right. So what we have then is dH dt is a, 20, over h, 10 root 85, times dA dt, 30. Okay? And that's that. I mean, 20 times 30 is 600. 600 divided by 10 is 60. So we can call this 60 over square root of 85. What are the units here? They must be feet per second, right? Because we're talking about just a distance, right? Feet per second. Yeah, this was feet, so the feet would cancel. But then this is feet per second. So yeah, so feet per second. About how much is this, though, I wonder? So we've got... so that's about 6.5. Alright, so about 6.5 feet per second. Alright. Very good, so that's that one. Okay, let's do another one. I have two more examples that I want to show you. So here's another one. It says a camera is mounted at a point 3,000 feet from the base of a rocket launching pad. If the rocket is rising vertically at 880 feet per second when it is 4,000 feet from the launching pad, how fast must the camera's elevation angle change at that instant to keep the camera aimed at the rocket? Oh goodness. I don't know. When I read through these things, my first instinct is to just feel panicked. But when I start to draw it out, it becomes more clear to me. So a camera is mounted at a point 3,000 feet from the base of a rocket launching pad. So I'm going to say the camera's here, and that the rocket launching pad is there. So this is the camera, and this is the launching pad. Okay, and that's 3,000 feet, right? 3,000 feet between those two locations. All right. If the rocket is rising vertically at 880 feet per second when it's 4,000 feet above the launching pad, how fast must the camera's elevation angle change at that instant to keep the camera aimed at the rocket? Okay, so you've got this rocket that's kind of exploded off this way, and it's going to be, you know, a certain distance from the ground. I'll call that distance y maybe, or you could call it h, whatever. Okay. The question that we're being asked is, how fast must the camera's elevation angle change? So, so the elevation angle of the camera is this angle right here, which I'll call theta. We want to know, so notice that as the rocket continues to rise, okay, the angle is going to have to change, right? The angle is going to have to change. And so the question is, how quickly is the angle changing at that particular moment when the rocket is 4,000 feet above the launching pad? So let's answer that question. First of all, we need to find a way to relate theta and y. And I think one way that we could do it is to use maybe the tangent function. Say tangent theta equals y over 3,000. Okay. And then what we want to find is the rate at which theta is changing. In other words, we want to find d theta dt. So if we differentiate this equation now with respect to t, right, derivative of tangent is secant squared theta, but because we're differentiating with respect to t, we have to multiply this now by d theta dt. And then derivative of y with respect to t is just dy dt, right? So this will be 1 over 3,000 times dy dt. Okay. So now the question is, well, I want to find d theta dt. So maybe what I'll do is divide both sides of this equation by secant squared theta. So I'm going to get d theta dt equals 1 over 3,000 secant squared theta times dy dt. Okay, now what do I need in order to solve this equation, or in order to solve this problem now? Well, I need to know what theta is, and I need to know what dy dt is. I know what dy dt is, right? dy dt is the rate at which the rocket is rising, and we're told that it's rising at a rate of 880 feet per second. So I can get dy dt pretty easily. Theta was not given to me. You can scan through the problem and you can see, right, like they're not telling you what the angle theta is. But what they do tell you is that when the rocket is rising at a rate of 880 feet per second, it's 4,000 feet above the launching pad, so that y is 4,000. So I'm going to draw another little right triangle here, kind of as some scratch work. Right, we've got theta, we've got 3,000, and then y is 4,000. And so we can figure out what theta is. Right, we can say, well, Well, and actually I don't really care what theta is, come to think of it. What I really want is, I want to know what secant theta is. Or better yet, 1 over secant is cosine, so maybe I can think of it like this. Cosine squared theta over 3000 times dy dt. So really, I don't even care what theta is necessarily, I just want to know what cosine theta is. So to find cosine theta, I would have to know adjacent over hypotenuse, right? So I need to figure out what the hypotenuse is. So we'll do some Pythagorean Theorem. Oh, I don't want to use the thousands. I'm just going to say 3 squared plus 4 squared equals, I'll call it h squared. So 9 plus 16 is h squared. That's 25, right? So h is 5,000, right? So from this I'm getting the 5,000 there. Okay, so what's cosine theta? Cosine theta would be 3,000 over 5,000, or in other words, 3/5, right? Okay, so d theta dt is 3/5 squared over 3,000 times dy dt, which is 880. Okay, so I'm going to pop that into my calculator. We've got 3/5 squared over 3,000 times 880. That comes out to 66 over 625. This should be radians per second, right? Because it's how fast the angle's changing, so it's in radians per second. Yeah, because here we had 3,000 feet, here we had 880 feet per second. The feet cancel, that just leaves, number per second, or in other words, radians per second. Okay, so this is radians per second. If we wanted to change that into degrees per second, then we could multiply this by 180 degrees over pi radians. That way the radians will cancel and leave us with degrees per second. So I can multiply this by 180. And that comes out to 2,376 over 125 degrees per second. Oh, how would I say this? Degrees per second, which is approximately what? Let's see. That's approximately 19 degrees per second. Okay, so that's that one. Let's move on to the last one. Okay, the last one says, suppose that liquid is to be cleared of sediment by allowing it to drain through a conical filter that is 16 centimeters high. So this is kind of like the first thing that we looked at. Allowing it to drain through a conical filter that is 16 centimeters high and has a radius of 4 centimeters at the top. Suppose also that the liquid is forced out of the cone at a constant rate of 2 cubic centimeters per minute. At what rate is the depth of the liquid changing at the instant when the liquid in the cone is 8 centimeters deep? Then I give us a little hint. Find a way to express the radius in terms of the height. Okay. Well, let's draw out the scenario. So we've got this cone. Right, this conical filter, it says. It's 16 centimeters high, and the radius is 4 centimeters. So The radius of this cone is 4 centimeters, and it is 16 centimeters tall. Okay, so we want to find the rate at which the depth of the liquid is changing. So in other words, as the liquid is forced out of the bottom, the height of the liquid is dropping, right? So, you know, maybe our liquid is down to here at some point, and we can call that, let's call it the height. We'll call it the height of the liquid. We want to know how fast that height is changing. So if I ignore my hint here for a second, we can relate the height and the radius and the volume and all of that stuff, right? Because we're told that the water is forced out at a constant rate of 2 cubic centimeters per minute. That's how fast the volume of water inside of the cone is changing. So that's dV dt. So we need to find a way to relate volume to radius to height, right? But as we saw on the first page, if I differentiate this with respect to t, what do we get? What did we get on the first page? We got pi over 3 times 2rh dr dt plus r squared dh dt. And we want to find dh dt. So we have dh dt, and that's good. But look at everything else that we need. We need dv dt, okay, which we're given, right? That's the 2 cubic centimeters per minute. We need h. We're given that. That's 8 centimeters, right? We're told that it's 8 centimeters deep at the instant we're curious about. We're not given r, but I think we could figure it out using some geometry, right? So we could figure out r, but then we would also need dr dt. How fast is r changing with respect to time? We might be able to figure that out, but I think it would take a lot of work. So instead of doing this, I'm gonna follow my hint here, and I'm first gonna find a way to express the radius in terms of the height, and that way, instead of having 2 variables to worry about, I'll only have 1 variable to worry about, and so I won't have so much missing information. So let's figure out how to express the radius in terms of the height. So at this point, you know, we'll call this the radius r, and here's what I'm going to do. So from this point down to the center of the cone, that's what we call the height h. If we continue this line up, then we see that from here down to the bottom of the cone is, well, it's 16, right? So this length is 16, and this radius is 4. So notice that these are similar triangles. Okay, this little triangle here is a similar triangle with the big triangle here, right? And so what that tells us is that 16 over 4, right? Similar triangles have proportional sides. So 16 over 4 equals h over r. And there you go. That's how we can express r in terms of h. So 16 over 4 is 4, by the way. And so that means r is h over 4. So I can replace r with h over 4 now. in this formula. So I'm going to bring this down here now and say, so actually v is pi over 3 times r squared times h. 4 squared is 16. 16 times 3 is 48. So I have pi over 48 times h squared times h is h cubed. So that's much nicer. Now if I differentiate that with respect to t, I get dv dt equals pi over, well, actually it would be 3 times pi over 48. But 3 goes into 48 16 times. So it would be pi over 16 times h squared times dh dt. Okay, and I want to find dh dt. I was given dv dt, that was the 2 cubic centimeters, right? That's the dv dt. And then I was also given the height, right? Or the depth of the liquid, right? So that's h is 8. So I'm going to say 2 equals pi over 16 times 8 squared times dh dt, which is what I'm trying to figure out. Okay? Um, 8 squared is 64. 64 divided by 16 is 4. Okay, so we have 2 equals 4 pi dh dt. That means that dh dt is 2 divided by 4 pi, or in other words, 1 divided by 2 pi. So it's 1 over 2 pi. And this should be centimeters per second, right? Centimeters per second. Let's see about how much that is. So dh dt is approximately 1 over 2 pi. That's about, we'll say 0.16 centimeters per second. Okay, and that's that one. Okay, so that's related rates. So that's that. See you in the next section.